super exciting to be giving this talk, especially after Aptos' highly anticipated mainnet release. So one of the things I think that makes Aptos unique is the Move programming language. And the Move programming language is a safe way to design and to code your smart contracts. And I think with Move, less vulnerabilities can be written, and people can have a lot more assurance in their smart contracts. So real briefly, who is Zellic? Zellic is the founder of the #1 worldwide competitive hacking team, Perfect Blue, in 2020 and 2021. And we also audited 7 Aptos projects before mainnet release. So we got a lot of good exposure to what Aptos code looks like and basically what the current ways of writing Move code are. Now, I think this will change as we see more projects in production, but as of now, we kind of got a good glimpse as to what the ecosystem looks like today. So, to keep things interesting, I figured let's jump right in and look at a simple smart contract in Aptos Move. So, as we see here, we have a module which defines a contract, and it's called property testing. And this actually refers to an address. So an address can be 32 bytes, but that's going to be super long, so we can use a named address that makes it a lot simpler on the eyes. So here's just a very simple contract. We can see we defined a constant, 2 functions, and some tests, and this kind of encapsulates a lot of what you can do in Aptos. So for example, we can define functions, we can import dependencies. So as we can see in this line, use Aptos std math 128, we're actually importing a U128 math library, and we're actually calling that function in our function power plus 5. And this is the way that we can get composability and interact with other Aptos programs, as well as write our own programs. So something that's actually cool here I want to talk about is the spec. So it says spec add 2 numbers, and this is a form of formal verification. So basically what this is saying is that test this function and take the return value of add 2 numbers, which is a plus b, and then ensure that the result is always greater than a minus b. So this is actually a lot more powerful than a unit test because this provided a truth value for every possible input scenario you could provide to A or B. So it is exhaustive on all input cases, and that's as opposed to a unit test, as we can see, test add 2 numbers, which is just a simple test, which is the result 20, and then the other one, which is expecting failure. But I think formal verification is a super cool part of Aptos Move that allows us to provide guarantees on the totality of function behavior, and I think it's something we're going to be seeing a lot in smart contracts. So yeah, the other example at the bottom is an example of a unit test that fails, but we can catch the failure. So these are just kind of the ways you can write code in Aptos and the different ways you can go about testing it. So why do we care about Move at all? So one thing that's super good with Move is that it's helpful for developer friendliness. So it ships with a rich standard library and framework. So if you want to write Move code, there already exists a lot of building blocks that you can use and base your code off of versus having to code that from scratch. And this is important because you don't want to waste time rebuilding the wheel. The deployment process is very simple. If you get the Aptos CLI, you can deploy code very quickly, and the compiler is very friendly. So if you've ever written code and you don't know why it doesn't work, it's a huge pain. And luckily, Move gives us very friendly compiler error messages so we can get our code working. Also, it's security friendly. There's no dynamic dispatch. So this essentially means you have to know at compile time what module is going to get called. So if you think about Solidity, if you can execute arbitrary code that calls into an arbitrary smart contract and Move, all that has to be known at compile time. Also, there's formal verification tools, as we've seen in the last slide, and there's an intuitive global storage model. So global storage, and we're actually going to talk about that more in depth in the next slide. And also, mass adoption needs consumer confidence. So security is very important because all these big hacks we've been seeing deters mainstream adoption. So it's really important we get good tools that encourage people to come in the ecosystem. And while the language can only do so much, there's still a need to do things correctly. So there's still a right and wrong way to write Move code, and hopefully we can get across some of those points. So one thing I think that's super important is understanding the global storage model of Aptos. And global storage is basically the area where data persists in the blockchain. So global storage is going to hold information like what user has how many of what coin. So for example, we can see at address 50, this user owns, so this is a resource identifier. So we see OX3 coin. So they own the coin at address 3, the coin, and they own the coin struct. And this is going to make a little bit more sense when we actually see how this is written in code. But addresses can own resources or they can own other deployed code. So this is if you actually deployed your own module. So this is just kind of the rough layout. So when we talk about storing and moving resources from different accounts, like envision this as the thing that's actually happening underneath. So core language features, we've kind of talked about this. We have Boolean and integers, which is just true, false, and then unsigned integers. And fun fact, there's actually overflow protection. So if we have a U8, which can technically hold 2 to the power 8 or 255, and you add 1, then you will get an overflow. But if you actually bit shift it to the left, then that overflow is not caught. So that's just kind of something we look at from a security standpoint. Then there's address and signers. So signer is a form of authentication in Aptos. So if you have a signer in your move code, then you do know that this user has signed a particular action with their private key and that you have some form of authorization, and you can define your move code and security model based off of whether you have an address or signer. Because an address can be arbitrary versus a signer has proven their identity. And we have vectors, which are arrays, which can hold groups of numbers. And we have loops, conditional logic, if, while loops. And then something that's unique to Aptos, or at least from if you have an Ethereum background, would be generics. So this is actually an interesting function that I think encapsulates a lot of what is different from Aptos from other blockchains, which these other presenters I know will be going more in depth about. But there's a module in Aptos called coin.move where you can create your own coins. For example, you want to instantiate your own coin to have some sort of value. The deposit function actually, as its second parameter, is taking the coin itself. And I think this is a fundamental difference between how Move works versus other blockchains, is that you're actually giving it the coin itself that you want to deposit to a particular address. And I think it's one of the features how Move kind of mimics the way we intuitively think about money. That's kind of what makes Aptos cool. It kind of matches our intuition on how you would already believe digital money should act. And then also there's custom data structures implemented in the Aptos standard library, like table, iterable table, optionals, which means the presence of a value or not a value. And yeah. So we have these resources that people store in people's accounts. Resources could be some certain token. So the way you're actually in Move code, going to take resources and transfer them to other people's accounts depending on certain actions is through these global storage operators. So if I was a smart contract developer on Aptos and I declared my own resource and I wanted to be able to move around different people's accounts, I would actually be using these global storage operators, and that's how I would achieve my functionality. So structs are actually define the schema of what your resource is going to look like in global storage, and they can also have abilities. And the formal definition of this is called linear typing of behavior. But long story short, if structs have abilities, this dictates whether they can be stored in global storage or not, whether you can duplicate them, whether you can drop them, and kind of how they're going to act within the Move program. So let's jump right in the weeds. So this is actually how you create your own coin on Aptos. So actually, if you notice, this function isn't public. You would actually call a public function, but that calls this function right after that. So this is kind of the guts of what's happening. So you call initialize internal. Now account's going to be you because you've signed this transaction. If you're the one that wants to create your own coin, then it's going to actually extract your address. It's going to check if you've already performed this operation. For example, if we see on the bottom line, we move to our account, all this coin info, then if that resource already exists, then this assertion statement is going to fail. Do we like a laser pointer or something?
No. But you can go on stage and point at it.
Sure. But what's also very interesting, I think, is at the very bottom, as we can see, we return three things. We return a burn capability, a freeze capability, and a mint capability. And capabilities are a very powerful aspect in Move, which essentially allow the owner of the capability to perform a certain action. So for this example, whoever initializes the coin gets three abilities typed on the particular coin they've instantiated, which these are details I guess you kind of get a little bit more familiar when you write Move code. But essentially, you can burn, freeze, and mint the coin, and all you have to do is pass a reference to your capability, and then your program has permission to do so. So we'll see that in the next example. So here's an example of us actually using our capabilities to burn, mint, and create coins. So for example, we call the initialize function, which actually called the function that we saw in the previous slide. This gives us our three capabilities. We create a resource that stores these three capabilities, and then we move that resource that stores all the capabilities to the signer, the person. In this example, you could just say that's us. And then hypothetically now, if we wanted to take that capability and mint coins, we would get the resource from the signer, which is us. We get the mint capabilities, and we can call coin.mint with the capability, which then grants us permission to actually create coins, and then we return that back. So this is just an example of how you can use capabilities to grant certain permissions, and how capabilities essentially work and move to access control functions. So yeah, this is just the under the hood what's going on with mint. So now that someone's initialized a coin, if someone wants to mint this particular coin type, which is what they're going to pass, then they'd actually have to provide the mint capability for that coin type. And if they don't pass that, this function is going to fail. So that's what keeps this safe from an unauthorized user actually trying to mint this particular coin. So this is more stuff on capabilities. So essentially, if we look at this function, this just shows you how nuanced you can actually make capabilities. So if you look at get capability type 1 function, we create a capability resource, and then we move that to the signer. And then here we do that with capability 2, except it's of a different type. It's of type 2. And in our test, we've declared some custom types, type 1, type 2. If you get the capability of type 1, you won't be able to call this function. And if you get the capability of type 2, you won't be able to get the function that requires the capability of type 1. So I thought it'd be interesting if we looked a little more into some code examples in Aptos Core. So one thing, I know this looks a little daunting at first, but what's something that's super cool is that their governance is all on chain. So for example, when proposals get passed, or when people want to make adjustments to the protocol, like let's change how long the block duration is, or let's change this certain feature of how this code works in production, then someone can pass a proposal. And the way you actually vote is it's going to check how much stake you've locked up. So it's proof of stake. So depending on the more stake you've locked up, the more power your vote has. So depending on how much you've staked in, it's actually going to modify that governance proposal to say how much voting power you had and whether you voted, whether this proposal should pass. So from a Move perspective, we can see, if someone wants to actually vote and vote on a particular proposal, you're going to pass into the signer. So this is actually passed at the VM level. You're going to pass what stake pool do you have stake in, because you only want the program's actually going to check that the stake, that you actually have the stake in the thing you're getting voting power from. Otherwise, that wouldn't make sense to acquire voting power from something you haven't staked into. And then it's going to borrow all. So borrow global mute is basically it's a global storage operator that's going to get a mutable reference to the particular type you have gotten at a particular address. So we're going to get all the voting records. We're going to check if this key exists at a particular vote. If it does, then it's it's going to add the key. If it doesn't exist, it's going to add the key. Then it's going to get your voting power, and then it's going to actually create the governance proposal. So I think it's just super cool how governance is implemented on chain, and how we can see in move code how something like that would be executed. So another example is pool. So imagine you had a pool of tokens, and that however many people deposited tokens got minted a proportionate amount of shares. How would something like that be implemented in move code? This is an example of that. So if the pool had 0 tokens and I deposited 10, that'd be minted 10 shares. So kind of what I wanted to focus on more on this was the logic of how this actually looks in move. So we're gonna take a particular pool, we're gonna have a shareholder, we're gonna have how many shares that we want to add. We're gonna check if the shareholder exists within the pool itself. If it does, then we actually don't want to add them to the list of shareholders because they're already in the pool, and this is just kind of just how it looks like in move code. So we can actually go by this line by line. So first, we have a mutable reference to pool. So we're gonna get that particular shareholder. We're gonna get how many shares they already have, and that we're gonna actually dereference the amount of shares. So this is kind of referencing the whole copy ability, which under the hood is gonna, a U64, any primitive data type can actually be implicitly copied. So we're gonna get that existing share, and we're gonna just check that we're not minting some absurd amount. That's what this is checking. And then we're gonna add the amount of shares that we want to mint, and then we're gonna return that. Otherwise, we're gonna check that the amount of shareholders is not greater than the limit we have, and then we're going to push back the shareholders and return the shares. So, long story short, this was a quick rundown on Move. I'm sure you guys have a lot of questions, but I hope this kind of could clarify how Move programs look, how they're a little bit different, and if you want to keep up with us, we're on Zellic, IO, and I'm Versatile Crypt.
Great. First, a round of applause for Varun. And we have a bit of time for questions. So if you have a question, raise your arm and use the microphone.
Hi, my name is Joseph. Thanks so much for the presentation. So I've been playing around with Aptos a bit, and so in Ethereum, when you instantiate a variable, there's a getter which automatically goes to read functions.
Right.
In Aptos, when you query you have to query a resource, or you can interact with a write function. However, I couldn't figure out whether there's a concept of read functions in Aptos. Wondering if you've managed to
So that you have something called view functions where you can just kind of see the state of the protocol. And I think you actually don't even have to implement view functions in your smart contract. Aptos actually, through their API, has a way of getting the state of a smart contract or the resource at a particular address. So I'm not sure if they've implemented that yet, but I think getter functions for resources are going to be accessible through their API.
Yeah, so I've managed to access the resources, but I've not managed to use a read function. I don't even know if it exists.
Like on the contract level?
Yes, within the contract.
I don't think it automatically generates a read function if you have access from another contract. I think you would have to implement that yourself.
Okay, thank you.
I think you had another one.
Could you go over more about like global storage and capabilities, as well as like the model of ownership, as well as I thought that was like a little bit. Could you clarify that to the world?
Sure. Yeah, we can go back to that slide.
Yeah.
So Move uses Rust ownership system, or uses parts of it. So I don't know how familiar you guys are with Rust ownership system, but essentially, if a function takes ownership of a variable, that variable is no longer in scope. So these global storage operators, as we can see, for example, you want to operate on the variable itself because we want that to be owned. We want that to be owned at this particular location. So if we look at this example, borrow global mute, if we were to actually borrow this variable and we weren't actually getting a mutable reference to it, then that variable would no longer exist in global storage at that particular spot. We want to get references to things when we don't want to take ownership of them, because when we take ownership of variables, they no longer exist in that particular location. So, for example, move to is going to take a particular item and actually store it at the signer, store it at that particular signer's address. And what's interesting with move to is that it actually, as we can see, requires a signer. So if it required an address, anyone would be able to move essentially resources to anyone's account. So this kind of shows that you need permission to actually get resources into your account. And so you said the ownership concept, and what else?
Like global storage.
Mm-hmm. Okay. Yeah, so I mean, global storage, these operators are kind of fundamental to how the language works, right? Because through these operators, we're going to be moving around resources in global storage. So person A, if Mike's smart contract wants to send this person 5 tokens, then it's going to be using these operators to actually do the transferring of resources. So that's kind of the purpose they serve within the move language.
Hello, I just got started on development and I used to be a Zellic developer. One thing that surprised me about Move is that once you get a signer in a function, and you can basically do anything like moving whatever tokens that is owned by that address, or like you can train every asset from the signer. Is that correct?
Right. So that is something from a security standpoint that it definitely needs to be looked at. That signer is very powerful. So for example, with access to a signer, you can do operations on the Aptos coin module. So one feature that I know Move is, or that Aptos in particular is supporting, is pre-transaction determination. I don't know the exact name, but essentially it is that before you sign a transaction, you're going to know exactly what that transaction will do, so that you don't have to sign transactions before. So you don't have to sign the transaction to essentially know what that is going to do, right? Because signer does grant you a lot of power, and you should kind of try to not use signer as much as possible. Yeah.
So that means the anti-phishing attack is done by the audit level, not the protocol. Is that right? The audit should pop up some notification telling the user that something is going to happen if you sign this transaction.
Wait, sorry. Can you say that again?
You hold it closer. Speak louder.
Oh, okay. I mean, it's the wallet duty to let user know that this transaction is going to have some consequences. And I think it's not from the protocol level to prevent this kind of phishing attack.
The wallet's duty versus who?
I mean, the wallet should let user know that the transaction could have some consequences.
Mm-hmm. I think wallets should support this feature because at the end of the day, the user is going to be interacting with the wallet and to submit their transactions. So I think if the wallet does show users what their transaction is essentially going to be doing, then that'd be a very helpful feature. So I think, yeah, wallets should be probably the first people to integrate this.
Thank you very much.
So we have one more question here, and then the last question after that. Anyone? No? Okay, go ahead.
So I'm not a developer, right?
Mm-hmm.
What's the reason why we're using the Move language versus Solidity or Rust? Is it because of security features?
I think security was definitely one of the main aspects or main influences in using Move. I'd say security is one of the big points, is because security and developer friendliness. So we wanted a quick way to be able to produce smart contracts, but security was definitely one of the big things in mind, because the formal verification tool example I showed you is actually kind of like a very powerful way in improving the correctness of contracts. So I think we kind of wanted to give users a lot more confidence in interacting with their programs and making sure that their funds are safe. So I'd say security was definitely one of the heavy influences.
Okay. Is Aptos Meta?
So Aptos actually, a lot of the core team, if I'm not mistaken, came from Meta, but then they sprung an independent movement to, I think, create Aptos.
Thank you.
I guess just to follow up on that, we've seen a few other chains, I think most notably Solana, say that at some point they're going to adopt Move. Is there a compelling reason why Move, I don't know, works better or is more native on Aptos as opposed to a chain that might just add it sometime in the future?
So I think one of the powerful aspects of Move was the bytecode verifier, and I think the Solana implementation of Move does not have this as of yet. And essentially the bytecode verifier means that you have the memory and type safety guarantees that Move gives. So I think as it currently stands, Aptos is the only chain that integrates Move in the way that provides the whole safety guarantees that kind of make Move a compelling reason to use in the first place. So I think if these other, what exactly was your question? Was there's a reason to like Move particular to Aptos versus other chains?
Yeah, was there something about Aptos that maybe leverages Move in a way that other chains that were natively built for Move will not be able to?
Yeah, I think it's the bytecode verifier has a certain level of safety guarantees that until other chains are able to incorporate that as well, these safety guarantees aren't as promised unless they have that.
Wonderful. Another round of applause for Varun. Thank you very much.